Hello everyone. In the previous lecture we have discussed retractions and we have defined, we have proved that the identity map and the inclusion map, they cannot be null homotopic if they are defined from S1 to R2 minus 0. Now in this lecture we will discuss Brouwer's fixed point theorem. But firstly, we prove a result related to non-vanishing vector fields. So first of all, what is a vector field? A vector field on B2, on the on the closed ball B2, vector field on B2, that is basically a pair. This is ordered pair x vx, where this x belongs to B2 and V is a continuous map of B2 into R2. So this is a continuous map of B2 into R2. So vector field is defined by this ordered pair x vx. So now V is a continuous map of B2 into R2. So it means Vx, that is basically an element of R2. And in calculus we use this type of notation. Vx is V1x into I and V2x into j, where I and j, these are unit vectors in the directions of x-axis and y-axis. They are basically standard unit vectors in R2. So this is the definition of vector field. Now what is non-vanishing vector field? A non-vanishing vector field is that vector field which is non-zero for every x. Non-vanishing vector field means Vx is non-zero for every x. Then we say V is non-vanishing vector field. In this case, basically, V is a mapping from B2 to R2 minus 0, because the vector field, in case of vector field, V is a mapping from B2 into R2. But because it is non-vanishing, it cannot be 0. So it is basically a mapping from B2 into R2 minus 0. Now, if we take this vector field V and we say that the vector field V points directly inwards at a point of S1, or we say there is a point of S1 where this vector field points directly inward. What that means? So vector field V points directly inwards at a point, let us say x in S1, then it means that Vx, this is basically negative multiple of x. So Vx is, if it is equal to Ax, where A is negative, then we say it points directly inwards. Similarly, points directly outwards. So if this Vx is equal to Ax, where A is positive. So Vx is positive multiple of x, then we say it is directly points outwards. So now we have this theorem. Given a non-vanishing vector field, on B2, we have to prove there exists a point of S1 where this point directly inwards, and there exists a point where it points directly outwards, where the vector field points directly inwards, and there exists a point of S1 where it points directly outwards. So we will prove it by contradiction. First of all, we assume V to be the given non-vanishing vector field, and we assume that V does not point directly inward at any point of S1. So suppose V does not point directly inward at any point of S1. So we will now prove that it will lead to a contradiction. So if V is a non-vanishing vector field, so basically it is a mapping from B2 to R2 minus 0. And let us take W to be the restriction of V on S1. Then W has an extension to the map V, and now this W can be considered as a map from S1 to R2 minus 0. So W is a mapping from S1 to R2 minus 0, which can be extended to this mapping V, which is from B2 to R2 minus 0. So we have done a theorem in which we have proved that if a mapping from S1 to X can be extended to B2 to X, then it is null homotopic. So basically this W is null homotopic by that result. So W is null homotopic, means it is homotopic to constant map. Now secondly, now we take J to be the inclusion map from S1 to R2 minus 0. Let this is inclusion map. Now we define a mapping F from S1 cross I to R2 minus 0. Now we have two mappings. One is W from S1 to R2 minus 0, and other is S1 to R2 minus 0, the mapping J. So now we will prove that W and J are homotopic to each other, and this F is basically a homotopy between W and J. So we define F by F of xt is equal to Tx plus 1 minus T into Wx, the line homotopy between X and Wx. For all X in S1, we define this mapping. Now this F, firstly, this is a well-defined mapping, means it maps all the points of S1 cross I to R2 minus 0. It means the image fxt can never be 0. Now we want to prove this thing, f of xt cannot be 0, so that the image fxt belongs to actually R2 minus 0. So first of all, f of xt, this is non-zero for t is equal to 0 and t is equal to 1. So when we put t is equal to 0 here, then we get fxt is equal to wx, and w is a non-vanishing map because it is restriction of v. And similarly, when we put t is equal to 1 here, then we get only x. So x belongs to S1, so it cannot be 0. It means f of xt is non-zero for all the t 0 and 1. But if t lies between 0 and 1, then fxt, if this is 0, now if fxt is 0 for some t lying between 0 and 1, then tx plus 1 minus t into wx, this is 0, then it will lead to wx is equal to minus tx upon 1 minus t. Now for any t lying in 0 to 1, minus tx upon 1 minus t, this is just a negative multiple of x. So we are saying here, if fxt is 0, then wx is negative multiple of tx. But we are assuming that v is the vector field which points directly inwards at no point of S1. That means there is no point of S1 where it points directly inwards. So Wx cannot be negative multiple of x. So this is a contradiction. So it means for t lying between 0 and 1, f of xt is non-zero. So this proves f of xt is non-zero. So it is well defined. Secondly, this is continuous mapping because it is defined in terms of line homotopy, so it is continuous. And then what is f of x0? F of x0 is just wx, and f of x1, this is just x, and this x can be written as jx for all x in S1 because J is the inclusion map. So f of x0 is wx, f of x1 is jx. So this is a homotopy between w and j, or we can say that w is a map which is homotopic to j. Now we are saying that w is null homotopic, and secondly w is homotopic to j. It means by transitivity j is null homotopic, means j is homotopic to a constant map. But j cannot be null homotopic because we have proved earlier that if j is inclusion map from S1 to R2 minus 0, then it is not null homotopic. So this is a contradiction. So it means there exists a point x of S1 where V points directly inwards. So this completes the proof of one part, that there exists a point where it points directly inwards. But for the point where v points directly outward, we take the vector field x minus vx. So now instead of v, we take this vector field x minus vx. Now if v is non-vanishing vector field, then minus v is also non-vanishing vector field. And then by this above result, minus v, then by this result, there exists a point x in S1 where minus v points directly inwards, which means vx points directly outward at that point. And this completes the proof of the result. Now using this result, we will now prove Brod's fixed point theorem. Now fixed point theorem, they are very important in the theory of topology or in mathematics. So we have this Brod's fixed point theorem. Brod's fixed point theorem that can also be proved by using methods of functional analysis, but now we prove here using this vector fields. Now this theorem says if f is a mapping from B2 to B2, and this is continuous map, then there exists a point x in B2 such that f of x is x, or in other words we can say a continuous mapping from B2 to B2 has a fixed point x. Fixed point means the point whose image is the point itself. So Brod's fixed point theorem says that the mapping from the closed ball B2 to itself, that has a fixed point. Again we will prove it by contradiction. So let us say there exists no fixed point. We will prove it by contradiction. So first of all, we assume that f of x, this is not equal to x for every x in B2. Then we define a vector field V by Vx is equal to fx minus x on B2. Because for every point x in B2, fx is not equal to x. So if we define Vx, fx minus x, then it will be non-zero everywhere. So basically this V gives a non-vanishing vector field, namely this x Vx on space B2. Then by our previous result, if V is a non-vanishing vector field, then it cannot point directly outward. Then by our previous result, there exists a point x in S1 such that Vx directly points outward at this point. So Vx is equal to, let us say, Ax for some A positive constant. But this cannot be true because so by our previous result, there exists x in S1 such that Vx is equal to Ax, which means fx minus x is equal to Ax. So it means f of x is 1 plus A into x. Now we are saying that A is positive, then 1 plus A into x, that is a point which lies outside the unit ball B2. Because A is positive, then 1 plus A into x. Now this x is a point of S1. So some constant which is greater than 1 into x, that will be a point lying outside the ball B2. So we are saying fx is equal to 1 plus ax. That means f is basically f is mapping this point x to outside B2, and that is not possible because the given mapping f is from B2 to B2. So this is a contradiction. It means there exists a point x in B2 where fx is equal to x. So this mapping basically has a fixed point. So now we prove an application of this Broad's fixed point theorem, and that is done in this corollary. Now we take a 3 by 3 matrix of positive real numbers. Let A be a 3 by 3 matrix of positive real numbers. Then this A has a positive real eigenvalue. So let us prove this result. Now here A is a given matrix, 3 by 3 matrix of positive real numbers. So let us define T from R3 to R3, which is a linear transformation whose matrix relative to standard basis for R3 is A. So this T is the linear transformation for which the matrix with respect to standard basis, that is A. Now let us take B to be the intersection of two sphere S2 with the first octant. Means B is those portion of S2 which is lying in the first octant. Means this area x1, x2, x3, where this x1, x2, x3 all are non-negative. So we can easily check that this B is basically homeomorphic to the ball B2, and therefore we can apply Brod's fixed point theorem on this B. Since any mapping from B2 to B2 has a fixed point, so this any mapping from B to B, that has also a fixed point by this Brod's fixed point theorem. Now, if we take a point X, X1, X2, X3 in B, then we can easily see that B is, since B is S2 intersection this first octant, then all the components X1, X2, X3, they are non-negative. And secondly, because this point X belong to S2 also, the sphere, then x1 square, x2 square plus x3 square, this is equal to 1, which means all these three, x1, x2, x3, can not be 0. All these three cannot be 0, so one of them is non-zero. So first thing we are saying that all of these x1, x2, x3, they are non-negative. And one more thing we are saying about these x1 and x2 and x3, that at least one of them is non-zero, means at least one of them is positive. So at least one is positive. So now the given matrix A has all the entries which are positive real numbers. So it means the vector Tx, that is also uh, a vector whose all the components are positive. So Tx is a vector whose all components are positive. Since the given matrix A has all the positive entries. So here, now if we define a mapping from B to B, let us say we define a mapping F from B to B by f of x is equal to Tx upon norm of Tx. Then this will be a continuous map uh, from B to B itself, because if we take a point X in B, then all the components of X, X1, X2, X3, they are non-negative, and at least one of them is positive. And we are saying that Tx is a vector whose all the components are positive. So if X1, X2, X3, at least one of them is positive, then all the components Tx, they are positive. So the mapping Tx upon norm Tx, that is well defined. And secondly, norm of this Tx upon norm Tx, this is 1, so it belongs to S2. And all the components are non negative, so this belongs to the intersection part, which is B actually. So this is a continuous mapping from B to itself. So by Brod's fixed point theorem, it has a fixed point. So there exists x naught in B such that f of x naught is equal to x naught, which means T of x naught divided by norm Tx naught, this is x naught, which means T at x naught, this is norm of Tx naught into x naught. So this equation says, this equation shows that T has an eigenvalue, namely norm of Tx naught. So T has positive eigenvalue, namely norm of Tx naught, which completes the proof of the result.